So guys, we begin with exercise 1 of the exercise series that we gave you. Here we are exploiting a typical application of the Zener diode as a sensor, a temperature sensor. The main parameter of this Zener diode is its sensibility, given by dVz over dt is equal to 10 millivolts per degree C. Another one is giving you a point of its relationship where Vz at 25 degree C is equal to 2.982 volts. So the studied circuit would be a voltage source. I think I'm gonna change the color. So the studied circuit is a voltage source E0 connected to a resistor with the Zener diode that is biased in reverse. We have Vz here, we have Iz going through, and R0. The first question, they ask you to calculate R0 in order to have a current that is equal to 15 milliampere at 25 degrees C. So just applying the KVL in this loop, you find that R0 into Iz, I'm gonna find the right color for you, R0 into Iz plus Vz is equal to E0, which means that R0 is equal to E0 minus Vz over Iz. If we apply this at a specific temperature, we will get E0 minus, for example, 25 degrees C, where we have all the information, over Iz at 25 degrees C, which means R0 is equal to 5 minus 2.982 over 0.015, which is equal to 134.5 degrees C. So this was the first question, asking you to find R0 for a value of the current at 25 degrees C. They then ask you to find the different parameters of the linear relationship between Vz of t and the temperature itself. This one is pretty easy, since the sensibility would be directly equal to, I'm gonna erase the circuit so you see my face while I talk. So Vz of t, A, is equal to the derivative of Vz towards temperature, which is equal directly to the sensitivity, which is 10 millivolts per degree C. And then if we apply Vz, the real expression at 25 degrees is equal to A times 25 degrees plus B, since C is expressed in Celsius. So 2.982 equal to 0.01 times 25 plus B, which means B is equal to 2.732 volts. In this case, we know the expression, the linear expression of Vz, it's equal to 0.01 times the temperature plus 2.732 volts. Now, if we continue with a different question, they propose a different circuit in figure 1.2, where they ask you to write Vs as a function of the different parameters of the circuit and its input Ve. So Vs at the output, this is a typical inverting amplifier, where Vs would be equal to minus R2 over R1 into Ve. Continuing with this one, we see that the second question, they tell you what happens if Ve is the Zener diode, is the output of the Zener diode, from the previous question. In this case, Vs would be equal to minus R2 over R1 into 0.01 T plus 2.732. Continuing with the different questions. So the third part of the exercise proposes a typical adder. Now you can either apply the equation or the expression of the output of the adder directly, or we can here, for the sake of exercising, for question 3.1, we can apply Millman at V minus. That would be equal to E over R4 plus V prime E over R3 plus V prime S over R5, which is over 1 over R3 plus 1 over R4 plus 1 over R5. Okay, so in this case you would also have V plus is equal to V minus is equal to 0, which gives you a direct expression of V prime S is equal to minus R5 over R3 V prime E minus, so minus R5 over R4 into E. So this is the typical expression of an inverting adder. The second question, they tell you that the input that was applied to resistor R3 is effectively the output Vs that was calculated previously, and they ask you to find values of R4 and R5 in order to have V prime S is equal to beta VE minus E. So if V prime E is equal to Vs that was calculated previously here is equal to minus R2 over R1 into, let's say we're gonna call it Vz directly. So we can, in this case, which is VE effectively, we can in this case write the expression of V prime S is equal to minus R5 over R3 into minus R2 over R1 VE minus R5 over R4 E. So V prime S would be equal in this case R2 R5 over R1 R3 into VE minus R5 over R4 into E. So this can be directly identified to beta VE minus E, and in this case for the conditions, beta would be equal to R2 R5 over R1 R3, and R5 would be equal to R4. So for the following question, they ask you to find, in fact they show you the whole circuit in figure 1.4 where they show the different stages, and then they ask you to find a direct relationship between Vs and the temperature, where you would have Vs prime is equal to, you can see it here, Vs prime is equal to Kt. So this means that Vs prime that was equal previously to beta VE minus E is equal to beta into, I'm not gonna replace them with their numerical expression until the end, AT plus B, that was VE with E equal to 0.01 and B the one calculated previously, minus E. So this means V prime S is equal to A beta T plus B beta minus E. In order to have V prime S is directly proportional to the temperature, This means E should be equal to beta B, and in that case K would be equal to A beta. If we do a numerical application, E would be equal to B, that was 2.732, into R2 R5 over R1 R3, and K in this case would be equal to 0.01 R2 R5 over R1 R3. Thank you.